Okay, so in the last class you saw this, main problem we want to solve is local minima in a grid, which means it's a 2D array n cross n matrix of integers, and local minima is defined in that picture. So the green cell in the center is a local minima because its 4 neighbors are bigger than that cell in value. So this always exists, and you can find this in single scan of the matrix in order n square time. So the question is, can you do it faster? So today we will see 2 faster algorithms. First one will be based directly on this 1D question that we have solved. So yeah, the 1D array is A elements 0 to n minus 1, positions 0 to n minus 1, and you basically divide it from the idea of binary search. Look at the mid and the neighbors of the mid minus 1, mid plus 1, and move to the side where you have a smaller value. Right, and we showed that this actually works, so its time complexity is log n. Any questions? So now you want to apply this to 2 dimensions from 1 dimension. Okay, so how do we do that? Any ideas?
So we also check the corner elements.
We also check what?
Corner elements along with the neighboring elements. We also check the corner elements. Like if we are going from up to one box down, we also check the elements which are from to the left of it and right of it.
Yeah, but you want to use this algorithm, the log n time algorithm. How will you use it in a matrix?
So there are 4 possibilities. We can go up and down, left and right. If we go up, we also check the neighbors of the cell which is up above the.
No, so what is the analog of mid in a matrix? So in here the mid was the middle element. What is the middle element in a matrix? Yeah, so you think of each of these entries as a column. So when you calculate the mid, you should be calculating the middle column. And in the middle column, you find the min. So min in the middle column is the analog of what we did here. That is how you will generalize this to 2 dimensions. So instead of cell, think of a column. So think of a column in the grid. Okay, so mid, so basically you will have now the matrix. There will be a left column, there will be a right column, and there will be a middle column. Middle column has how many elements? N elements. But there is, everything is so arbitrary that to find the minimum in the middle column, you have to spend n time. Right? That you cannot avoid because the grid is completely arbitrary. There is no sorting, there is no order whatsoever. So that will be order n time. So let's analyze that and see what we get. So you will consider in any iteration or any in a screenshot of the algorithm, what you will see is at any step you will see all the rows and columns from L to R. And so the middle now will be, I mean, same value L plus R by 2, but now this is considered as the column. So star refers that all the values on the row, which is 0 to n minus 1. And L to R are these columns, and middle is the middle column. So this is now a sub-matrix of your original matrix. It's a subgrid. Right, and here you want to do now this this decision you have to make which way to go. You have to whether you bring R backwards or whether you push L forwards by looking at mid minus 1, mid plus 1. Right, so that is now a two-dimensional thing. It's not as simple as just comparing three elements and picking the minimum. So we have to draw more pictures here. So find the min in this G star mid. Right, which will require order n time. Because these are basically, it's an array of n elements. 0 to n minus 1 is the value that star takes. So if this is confusing, it's the definition of this is just min I gi mid. And I goes from 0 to n minus 1. Okay, so this is order n time algorithm to find the min, because you cannot do anything better here. So say this is, this value that you get is GR mid. Okay, so R is the row where the mid is achieved, the min is achieved in the middle column. So we'll now focus on this element. So you have the L column and you have the Rth column. And you are looking at the middle column. And the ones before and after. So if this is your entry, this is the Rth one. So you have to focus on these two. Right, so this R comma mid is the entry which is minimum in the middle column. So inspired from the 1D array idea, you have to now focus on these two red cells, which are the neighbors in the column previous and the next, in the same row R. And so the decision you want to make is which half to go, right? Whether to go to L dot dot mid minus 1 or mid plus 1 dot dot R. So how will you decide this? What is your first guess? Whichever is smallest of these three, you go there. Right? And what happens if the green cell itself is the smallest? Right, so that is the simple case. So if GR mid, or let me say, calculate the minimum of these three. Yeah, so that's a new thing. So so GR R mid minus 1 mid and GR mid plus 1. So find this minimum of the three, and if the minimum is the mid already, then you will just output P. Right, because then you can see that in the full matrix, this or at least the matrix from L to R, this the green shaded cell is already a low, because it is smaller than both these red neighbors, and it is obviously smaller than the one above and the below. It's smaller than these two also, the green ones also, right? Because in that column you found the min. So since it covers all the four neighbors, you can output it safely. That is the answer. So obviously this will be an easy case. The hard case is that it won't happen. So suppose what happens is P is actually GR mid minus 1. So it will be either mid minus 1 or mid plus 1. What do you do then? So in this case you should take this half. So this becomes your next half to search recursively. Right? So based on which red cell in the neighbor is smaller, you move to that half. So which means that in this case you will be updating L or R. So R becomes now mid minus 1 and L remains the same. Right? So say P is this, then you can update R to mid minus 1. So basically what you are now focusing on so now you will search in G star L dot 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 mid minus 1, which is now the new R. Okay, so this R new is your mid minus 1. So now you'll be going from L to mid minus 1 and all the rows in that. Yeah, and so on. So this is again the binary search in 2 dimension. Why will it work? You have to give the proof of correctness for this. So you have to find, or you have to formulate the correct invariant, the correct property which is invariant. So for that you have to basically focus on the 2 vertical columns which are at the end. Okay, so you have to say that within these 2 vertical columns there is an element which is smaller than everything in these 2 end columns. So you observe here that this, when you move to the left red part, which is now this. So when you move to this red cell, this element is smaller than the mid column. Every element there is bigger than this red cell, right? So you have a stronger property now. Not only is it smaller than the neighbor, it is actually smaller than the whole border. So this vertical border on the right, every element there is actually bigger than this red cell. And the same thing you can assume for the left border, which is the Lth column. Every element there is bigger than No, so it will not be in comparison to this red one. So what you want to see is lemma 2 here. It will be a statement of this type. So the red one is smaller than its right column, and similarly the left column, if you move to the left, everything there is smaller than some element from L. So let me write that expression down. So that version of lemma 2 you want here. So what you want is to formulate an invariant similar to the 1D lemma 2. Okay, so that new lemma here will be as follows. So what I'll say is G star L minus 1 is greater than the minimum on the left side and minimum in the rth column is less than if you move to anything on the right. So once we have done the update, once we have moved to the R new, you can check that the second inequality is true by that step. So the minimum in the new right is that red cell, right? And that is less than the minimum in the column R plus 1, because that was the green neighbor of the red cell, right? So the second inequality continues to hold. In fact, this was the reason why we picked the left half. And symmetrically, the first inequality will also hold. Yes?
So does that mean that the minimum of the rth column is smaller than the global minima of the R plus?
That we don't know, right? We haven't even seen the submatrix fully.
So how can we write this statement?
No, maybe the definition of min L is not clear. Min L is just the location of the minimum entry in the L column. It's only a statement about the Lth column. Row where min of G star L resides. It is just the row where the minimum of Lth column resides. Just like min R was, in this picture, min R was smaller. I mean, we took the mid and then we took the min of the mid column. That was the row R. This mid now has become R plus 1. Or, actually the R plus 1 is your, has become the boundary now. So this is the left boundary. This is just outside L. And this one is just outside R. Okay, so just on the left of L and just on the right of R. So just focus on the second inequality. I mean, you don't have to worry about both of them simultaneously. You just see what you are doing in this one step here in this example case. So in the example case, you are only bringing the right border on the left side. You are picking the left half. So the R new that is mid minus 1 and R new plus 1 is mid. And you can see that in just these two columns, the property holds.
So does the red cell and the green cell have to be in the same row?
No, in this mid minus 1, the min can be anywhere, right? It can be, min can live here. Yeah, maybe that is also a confusion. So the min, this for example is min R in my notation now. So this is min of R new.
But how do we find this?
Oh, you are not finding it. You are just deducing. You have only found the green and the red cells. The blue one you will not find, you will just deduce. The blue one is even smaller than the red one. So the inequality holds true with blue also. The blue one is smaller than all the green cells in the mid column. You don't have to find it, it's already true.
How is that?
Well, because the minimum is smaller than the rth one, and the rth one is smaller than the whole column of mid. That's all. I mean, we are simply using the transitivity of less than, right? Everything is less than. So red is less than green, and blue is less than green, is red. Blue is less than red. So that's all. So this is less, and this is also less. So which means that blue is less than green. Now green is less than every other element in the mid column. So blue is also smaller from every other element. So we are only working with less than symbol. Is that clear?
Like the green cell is the global minima of.
No. There is no such claim. We are doing a we are just exploring the grid. We have not, the algorithm is not finished. So this is why you have to identify an invariant which holds true at this point and at every point. So that invariant is this lemma. This lemma will hold true right now, although the algorithm will continue to run. Okay, so this is the two-dimensional version, which you can see is quite complicated, and we are not done yet. So we'll make it even more complicated later. But let's first say something about the proof here. So example step. As done above. That updated R by moving to the left. Okay, so just in that setting, I mean, you only have to understand this one setting because the other one is symmetric. That will not require any new idea. So just focus on the step which was there on the previous slide, which moved to the left half by updating R. And there you can see these, the minimum P that we calculated and then we made the decision to move left already means that the minimum of the new R is less than the small r that we picked. That's in the rth column, which is actually in the picture it was the mid, and which is less than r plus 1. And this rth, small rth element in r plus 1 was the min of the whole, so which means that it is less than everything. G star r plus 1. Okay, so this is the old mid. In the picture. So in the picture, this r plus 1 is actually the old mid. We found the min of that small r row. So it is by definition of minima smaller than G star r plus 1, which then is greater than the neighbor on the left of it, which is less than the minimum in that column now. Right? So this is the sequence of inequalities. So we have proved the second inequality. Second bound, and first is symmetric. Okay, so these two you do, and then the proof is complete. So this is the induction step. What is the base step? In the base step of these inequalities, what may happen is L may not have an L minus 1, or R may not have an R plus 1. Right? This is what you start with. You start with L equal to 0 and R equal to n. So there are no, there is nothing outside them. Before 0 there is no column, and before and after n there is no column. So in that case, inequalities are true vacuously. I mean, in other words, you can initialize the L minus 1 thing to infinity and the R plus 1 thing to infinity. Right? So vacuously they are true. So base case is definitely true. When you do the induction step, then you come inside further, and then this proof kicks in. So maybe I should say identify the base case. So just to understand the setting, what we are doing here, you also should identify as an exercise the base case. And together they will mean that induction completes the proof. And this induction is on what? What is the thing which is changing? Sorry? L and R. Yeah, so what is changing is number of columns. So this is induction on number of columns. So you can see that the number of columns here is always halving. So if you started with n, then ultimately it will become 1. Right? So, well, that is okay. It's going too far. Here we only meant, number of columns is halving. So we are reducing the bigger theorem to a smaller case theorem, and by that it holds for all L and R. Yes, so that is the first lemma. That's the main important invariant. That's the only invariant actually. So you have to prove the lemma of invariance, and next comes the lemma of number of steps. but that is now easy. So this algo halves the number of columns. So it stops in log n steps. Right, so it will converge very fast to a single, it will ultimately converge to a single column. What will be the output now? What should you output? That is not clear at this point. You cannot output the whole column. You can output only one element, right? So what is the local minima that you got? So just look at this invariant as you looked before in lemma 1 and 2. So L and R have become equal, right? So min L and min R are equal, they are the same row. So just output that element. And so this is the second part of it, that G min L is a local minima. When you will reach L equal to R. Is that clear? So that is what you output. And this proof is direct now from the previous proof, because so G star L minus 1, everything in L minus 1 column is bigger than this, which is smaller than the second inequality, so G star R plus 1. So this compares in the same row. So in the same row you can see that in this min L row, both these neighbors are bigger, and when you look at the neighbors which are above it and below it, they are also bigger because you have taken the min in that column, right? So this is also less than So first one is by the lemma, and the second one is by just the property of min L. I mean by the definition of min L, in fact. So now you have covered all the 4 neighbors. So this is a local minima. And time complexity is easy. So number of steps is, well, not number of steps. Let's say number of recursive calls is log n as we are halving the columns. Each time. So that's about the calls. Okay, so there will be log n many recursive calls, and you still have to see what time is invested in every call. Yeah, so you have to calculate min L or min R. So that is again order n, because we have an unsorted random array. So that's the current theorem we have. It's already a big improvement on the brute force idea. This is found in order n log n time. So proof is just log n rounds or calls by the previous lemma, and in each call or in each round, number of steps or time is it takes order n time to find the min in the mid column. Okay, so just because of that, this is order n times order log n, which is that, as you have seen in asymptotics, order n log n. Right, so this is a tremendous improvement on n square. So this is now same as sorting, but here it's more impressive because it was actually an n cross n matrix. So this was like, you can't do sorting here because the input size is n square. So for input size n square, we are doing actually only n log n. So clearly we are missing the input. Much of the input we did not even see, and still we are able to give an answer, right? But we are not easily satisfied, so now we want to improve this further. So how do you improve this further? So let me just write an expression. So we have I equal to 1 to log n. These many calls are there. In each call we are spending time order n, which becomes order n log n. Right, this is the reason for this log n multiplier. So clearly, to improve on this, we have to reduce the summoned. The summoned order n we have to reduce. So can that be reduced? Which is, can the min be found faster? As you know, it cannot be found faster if as long as your array is size n, you have to spend time n. So which means that you have to halve the column size now. How do you do that? Well, for everything you say binary search. But what part of this picture will change? In this picture, you are only working with columns and they are all of length n. Yeah, so now once you have come to the middle column and decided to move to the left half, now is the opportunity to actually look at the middle row. Yes, but at what place? Will you do only for row, only for column, or both? Yeah, so you will do it alternatively. So right now we have done column, move to the left half, and in the left half now you look at the middle row and decide whether to go to the upper half or the lower half. So that will now simultaneously halve the space for finding min. Right, that would be the first idea. So we basically want to reduce in this calculation. So we are doing sigma n, I going from 1 to log n, and that is why we get n log n. We want to reduce it to something like this. So what is this? If we, instead of summing only n's, if we also halve them successively, what will this become? Yeah, so this will become, I is going from something 0 maybe. It's basically, it's even smaller than 2n, so you can write big O of n. Okay, even if you go to I equal to infinity, you can show that this sum is actually only like 2n. Right, so you use this high school inequality as an idea to develop a new algorithm. And that is why you need to now halve by taking middle rows. By taking the middle row and picking upper or lower halves instead of left or right halves. Right, so this will simultaneously reduce both the dimensions by half every time. So hence the time will now be in the ith step, ith call, it will only be n by 2 raised to I. So, and do this alternately. So alternate between column halving, number of columns halving, and number of rows. So you have seen the idea to halve the number of columns. Next, so once you have halved the number of columns, now you should halve the number of rows. Right? This is you do this alternately. So the problem that will happen is with the invariant. Okay, you have to show that these two inequalities and maybe more. So this is not, this invariant will not generalize for free. So that is the question, what is now the invariant that you are looking at? And does the previous algorithm already work? So does the previous algorithm idea so directly meaning that now when you take the middle row, in the middle row you will find the min and again look at its neighbors up and down, right, and then decide by the minimum of these three whether to go to the upper half or the bottom half. So will that algorithm work? Is there anybody here who says no? So that it won't work. So find a counterexample where it doesn't work. Okay, just doing the same thing on column and then on the rows will not work. So the reason is again, okay, let's go to the picture maybe. So the invariant we found by saying that these two vertical boundaries, I mean, you have an element inside which is less than everything in the outer vertical boundary of that. And when you will do this on the row, you will get a different condition. You will get a condition on, you have picked an element which is smaller than the horizontal boundary, which is just outside. You won't be able to combine the two. So the statement about the vertical boundary and the horizontal one, it is not clear how to combine it. In fact, I mean, if you just do this algorithm, it will fail on some examples. So there will be counterexamples to this example, to this simple modification. So find an input instance where the column boundary condition or invariant followed by the row boundary invariant doesn't give the right answer. Okay, so if you simply, the problem is that you will have too many inequalities. So you are comparing with you want a more integrated invariant instead of these invariants which are looking at, sometimes they will look at the vertical one and sometimes they look at the horizontal one. So that will not work. For example, there may be stupid things like this red cell which is, or the red or the blue ones, maybe both of them are lying in the bottom half, but you decided to pick the upper half. Okay, so when you pick the upper half, the bottom half condition is now lost. So when you will halve this by the row, middle row, you may actually lose the invariant which was true before. So this is why you can't have two different invariants acting independently. Then one will actually try to stop the other. So you want an integrated invariant which works for all. So this column invariant can get violated when you use middle row. And similarly, the row invariant can get violated when you use the column, the middle column. Okay, so this having two independently behaving invariants will not work. So next time we will see a much smarter idea, which will look all of these things as a whole, and then try to preserve that.